Okay. So instead of going through here and calling on you guys, I'm going to try to save a little bit of time, and I'm just going to basically give you the answers, okay? So number one uses something called Newton's method, and Newton's method is a technique that we use to approximate zeros, and we teach this in chapter 2 at the very end. In fact, I covered this year with you guys. And after 2 iterations of Newton's method, you should get about 17 over 12, or what's 1.417. Again, Newton's method uses this formula right here. So we basically you could use the mean value theorem to derive this formula, but there you go. So it's x sub n plus 1. The next closest guess is the last guess minus the value of the function at the last guess, divided by the derivative of the function at the last guess. Anyways, so that's the formula. Question 2 uses something called Euler's method. We use Euler's method to estimate solutions to differential equations. It actually turns out that there are many differential equations that we literally cannot solve. You cannot separate the variables to get the solution that you need to do. So you might need to approximate the solution of that differential equation. And so here's the formula for that. So y sub n is equal to the last y plus the step size times the value of the differential equation evaluated at the previous value of x and y. So in this particular case, our initial guess, I think I said, was 1. So after 1 iteration, you get a 0.9. 2 iterations, you get 0.82. 3 iterations, you get 0.758. So that's just some examples there. We could keep doing this, and the more of these we do, the more accurate answer we will arrive at. And finally, and I think differential equations, that is in chapter 5. That's chapter 5. And then finally, arc length, that was in chapter 6. It was the very last section in chapter 6. In fact, our test on Tuesday, and I guess, what am I talking about? I didn't record Tuesday's lesson because you guys took a test on Tuesday. Tuesday, we had a question or two maybe on arc length, and our formula for arc length is little s equals the integral from a to b. Sorry, my phone is ringing. Integral from a to b, square root of 1 plus f prime squared dx, and you will get an answer of approximately 248.067. Even though this integral looks kind of harmless, and you may be even tempted to try to do trig integration or trig substitution on this, I would encourage you to not try to integrate that one. This is, it looks very simple, and I should be able to integrate. Good luck with that. And if you don't believe me, I would just encourage you to go Wolfram alpha that integral and check out the work. It involves some pretty heavy-duty mathematics. It's kind of beyond the scope of this class, so I just used a calculator there. Any questions on the warm-up? Okay, so I'm going to move on. If something comes up, please feel free to either unmute yourself and stop me or put a question in the chat. Oh, by the way, this graph right here is the graph of this function 2x cubed plus 7. So if I want to know the distance, and you know what? I'm not sure I'm going to be able to get to this. Guys, I'm going to have to step out here for a second because I've got to get that mark off the bottom. Sorry about that. Last period I was using some technology and it put that the toolbar there on the bottom, which is nice to have. But anyways, back to what I was talking about. We are integrating, I think it was from 1 to 5. So we're talking about from here to 5, which would be way up here. So it turns out that that distance is about 248 units. And just to give you some idea, here's 1 and here's 5. But look at my y-axis. I had to scale that up to 250. So there's your answer for that one. Okay, let's go ahead and move on. General overview. Here's the general overview. So this is what you probably are most interested in this coming slides is what will be on the final exam. So here's what you need to know. Number one, it will be 75 minutes. That is the time of the class. So that is how much time you're going to have to take the final exam. So if you have any issues with the timing of that, I would highly encourage you that you communicate that with me before the exam. There will be 2 parts. There will be a multiple choice part, and then there are going to be 2 free response questions on this final exam. So multiple choice and 2 free response questions. By the way, I probably should mention this now. The free response questions, you will work those out on your own paper, or if you want to type it up in your computer, I don't care, but you're going to have to either probably take a picture with your phone or something like that to submit the answers, okay? Topics. So this is the part where you guys being BC students, you guys unfortunately, I just went over my AB class and they just did chapters 1, 2, and 3. That's all we got to this semester. You guys, basically anything from chapter 1 to chapter 7 is fair game. Chapter 1 to chapter 7 is fair game. Last year, you would have went through chapter 1 through chapter 6, basically. So really chapter 7, these advanced integration techniques, which is what we just had a test on, that's the only thing that's going to be different maybe from last year, except for, the other couple of new things that we did was arc length and surface of revolution. We just talked about that. And then, of course, I threw Newton's method and Euler's method. So, guys, I'm trying to intentionally put things here today that are things that maybe wouldn't be from the AB curriculum, okay? And I guess I should say this. The majority of the exam is going to be chapters 3 through chapter 7. Those are the main ideas I'm going to be hitting. I'm not really going to, there could be a question on, what's the derivative of this thing using the chain rule, but it's really going to be starting with chapter 3, which is applications of derivatives. Does that kind of make sense? Shake your head yes if that kind of makes sense. Okay, cool. All right, so some more details. There will be exactly 15 multiple choice questions. There will be 2 free response questions with subparts. Now, here's what I'm kind of thinking. I'm thinking that if you spend, let's say, 15 minutes per free response question, then that means you're going to spend about 30 minutes here. Does that make sense? Because that's what we kind of budget when we do the AP exam. And then if you have 15 multiple choice, let's say you do 3 minutes per each of those questions. So 3 times that, that'd be 45. And then guess what happens when you add those 2 guys together? You get about 75 minutes. So that's kind of how I structured the exam. All right. Now, there could be multiple choice questions that you get done in a minute. There might be some that take 4 minutes, but on average, I assume it's going to take about, and by the way, these are a variety of things from any of the chapters. So I'm assuming you're going to spend about 3 minutes per problem, and then I assume you'll spend about 15 minutes per free response. Okay? You should be proficient at using calculator type things for calculus. So, and I might go ahead and do that right now. I'm going to keep this. I'm going to go to the Canvas page, which hopefully is right here. Is this BC? Yes, this is BC. I'm going to go all the way back up to the top of BC very quickly. Look at all that stuff we've done. But up at the top here, this is where I do all of my, like what we did on December 1st. There's a video. This is the in-class stuff that we did. But what I want to show you now, these are the things that you guys have asked me about, or things that I thought, hey, you know what? They might need to know how to, I know this sounds silly, convert a decimal to a fraction or vice versa. That might be handy. Or how do you, it says hot. I probably need to fix that. That's not hot. Let's not, hot's probably not the right way to say that. How to graph a piecewise defined function. Anyways, you get the idea. So please make sure you know how to use your calculator to do the calculus-y type things. Okay. Also, as you guys already know, make sure if you have to do anything with a decimal, particularly on the free response, make sure you go out to at least 3 decimal places. Don't give me 2, and certainly don't give me 1. Unless it asks you specifically to round, you need to go to 3 decimal places. Okay, so let me stop there. Questions or comments about the final exam? Okay. And guys, what I did when I created this exam, I just basically tried to go through and strategically pick. Like, it's not heavy chapter 7, it's not heavy chapter 2, or not chapter 2, chapter 3. I tried to get a little bit of the best things from everything. Okay? All right. So now what I'm going to do now is I'm going to just kind of review chapter by chapter, starting with chapter 3. I'm not going to go back and talk about limits, even though you guys should know that. And I'm not going to go back and talk about how you do derivatives. That's stuff that, and honestly, you know most of this as well. So chapter 3, we had 6 sections. I'm not going to read through all of these, but things like extrema, the mean value theorem, the first and second derivative tests, curve sketching, this is useful. I mean, oops, go back to that. Sorry about that. Curve sketching is kind of a definite something that I think students need to be aware of, but I'm not going to ask you to sketch a curve on the final, okay? But what I could do is say, where's this function increasing and concave up? Which, by the way, is covered in these 2 things here, right? So curve sketching is just kind of the application of that. And then, of course, optimization problems, which in my opinion is actually one of the most important applications of differential calculus. How do we figure out how to maximize profit? How do we minimize this or whatever? So that's chapter 3. So some big questions. What are extrema and why do we care? Anybody want to answer that? Okay, I'll answer it. That's what I just said. Extrema, that's where the high points or low points are. So if I'm trying to maximize the profit of a company and I've got some curve that shows, the money that they make, and I want to find, hey, I want to maximize my profit, let's say, this is how I do it. I would be looking for extrema based on that model. Or if I wanted to maybe, let's say, minimize the taxes that I have to pay. So that's what extrema is. That's why it's important. They're the high points and the low points, if you will. All right, another question. How do we reduce, this is actually probably the most important question. How do we reduce the number of, and I should have put the word possible locations for extrema. How do we reduce the number of points we have to check for possible extrema? And it boils down to 2 words.
Critical numbers?
Allie, you are getting my mental gold brick right now for saying that, because I think that's why we use the term critical. Guys, how many points are on a curve? Infinitely many. We don't want to check infinitely many things. We only want to check those numbers that are critical numbers. So this is critical in terms of importance, and we use the first derivative of the function to find those critical numbers. We set the first derivative equal to 0 or d/e. Who can tell me what the key, and this is like almost ridiculously silly question. What's the key difference between the first derivative test and the second derivative test? Allie, you can't answer this one. You already got the mental gold brick for the day.
One uses the first derivative and one uses the second derivative.
Man, that is so insightful. Thank you very much. So basically, if I'm looking for extrema, I plug the critical numbers into the first derivative to use the first derivative test, and I look to see if there's a change in sign. If I want to use the second derivative test, I plug the critical numbers into the second derivative and determine if it's positive or negative. Now, don't forget, it could be that the second derivative evaluated there is 0, in which case you have to go back to the first derivative test. Okay, chapter 4, integration. Big ideas, antiderivatives, areas, Riemann sums, FTC, U sub, log integration, and inverse trig integration. So that's chapter 4. We covered all of those things, and we spent a lot of time on that last year. So there's chapter 4. So big question, what the heck is an antiderivative? I'll answer that one. It's the opposite of the derivative. So it turns out that we find out that the fundamental theorem of calculus basically tells us that there's this inverse relationship between integration and differentiation, and an antiderivative is just undoing a derivative. By the way, how do we check our answer to an indefinite integral problem? How do we check that answer?
You do the derivative of the indefinite integral.
Exactly right, James. So just like we just talked about, the antiderivative is the opposite of the derivative. So if I do if I do an integral and I want to check it, just differentiate it and see if you get back to where you started. Who can tell me what the key components are of FTC? Key component, and I think the wording on that's not very great. I guess what I'm asking is there's a couple of parts to FTC. What are they? There's two parts. There's FTC part 1, there's FTC part 2. What do the two give us? And they're different. They give us different things.
FTC part 1 is you can do a definite integral from A to B, where you do the antiderivative evaluated at A to B.
Perfect. Anybody want to give me part 2?
Yeah, I'll also give part 2. Part 2 is the d over dx of the integral a to x equal of f of t dt equals f of x.
Perfect. So part 1 allows us to evaluate the definite integrals from A to B, okay? The second part is simply going back to what I said a second ago when I said the FTC gives us that, hey, the derivative and the integral are inverse operations. So that's what the second part is telling us. If differentiation allows us to calculate the instantaneous rate of snowfall, then what does integration do?
It tells us how much snow fell.
Perfect. That is exactly right, Mr. Boston. That is exactly right. Differential calculus gives us the instantaneous rates of change. Integral calculus tells us how much accumulated, in this case, snow. That's exactly right. Okay, good job. Let's move on. All right, chapter 5, which is, I think, maybe the shortest chapter. Chapter 6 is pretty short, too. So we dealt with slope fields, and there's that Euler's method. Separation of variables. So those are solving differential equations. And then the logistics equation we covered. Notice I skipped section 5.2. I did section 5.2 in Calc 1. It's an important section. It basically involves exponential equations. But anyways, we're going to move on from that. So let's look at some key questions. What are differential equations and why do we care? I will answer that one because this is a big, big problem. It turns out that almost any in fact, I think any dynamic system in nature, in the world, on the internet, whatever, any dynamic situation can be modeled by a differential equation. And a differential equation is simply an equation that has a derivative in it. And so why do we care? Well, we want to be able to solve these differential equations. Now, the bad news I've already mentioned is you can't always solve every differential equation, and you might have to do something like Euler's method to approximate solutions. Now, I'm going to tell you right now, I won't ask you to solve a differential equation using Euler's method, or I guess I should say approximate, without telling you, hey, you need to approximate. But it is true. In fact, if you go into mathematics at the collegiate level, there's a course on differential equations, an entire course on it. And then if you get going beyond that, at the grad level, I took a class on qualitative reasoning, which was even beyond that. So there's actually most higher level mathematics and most higher level sciences, they pretty much, that's all they do is differential equations. Okay, so what's the difference between a particular and a general solution?
One of them gives you a number and one of them gives you an equation.
No, that's not true. It could be true, but in general, no pun intended, that's not the case.
One usually has like plus c, and one will have the specific y-intercept.
Correct. That's the difference. So the general solution is going to be some sort of equation plus a constant c, the constant of integration. The particular solution, so by the way, when you get the general solution, that is the whole family of curves. That is the solution to the equation. Where the particulars, they say, oh, I don't want all of them, which by the way would be infinitely many of them. I only want the one that goes through 2, 7 or whatever. What is the most important step of solving a complex differential equation? And when I say the most important step, I'm going to say it's the most important step on the AP exam.
Separation of variables.
Exactly, Mason. That is exactly right. We've talked about this, and I hope if you have Mr. Brewington last year, he talked about it too. On the AP exam, they like to give on the free response a differential equation that involves separation of variables. if you do not separate the variables at the beginning, you get a 0 points for that. So please make sure you get separation of variables. Why is the logistics equation perhaps a better than the exponential equation?
It represents a limit on growth, whereas the exponential equation doesn't have a limit.
Yeah. So, for example, here on Earth, can we have infinitely many human beings? The answer is no, because we have a finite amount of size and a finite amount of resources. So we can't truly say that the population of the Earth is exponential. It's going to have to be logistic. And it's interesting. There have been a number of predictions of, we can only support this many humans. And now I think we're up to close to 7 billion, 7 billion, I think is the number. And at one point they thought 2 billion was going to be the max that we could have. And I think China alone has 2 billion now. So anyway, so that's the logistics equation. Okay, chapter 6 has 3. So area between two curves, which I kind of skipped over that. We kind of jumped right into the disk, washer, and known cross sections. And then this was certainly new right here for this year. This is the arc length and surface of revolution problems, which you guys saw that on the last test that we took. So some big questions here. What is the basic formula in both the disk and the washer method? I'll give you a hint.
Integral and then integral.
No, I don't want the integral. Pi r squared. Both of these, we're talking about revolving it around an axis, correct? We're revolving this around an axis, and then we're slicing it. Each of those slices is making a disk, and a washer just means we're taking the big disk and the little disk, and we're subtracting the inner disk out. Now, I don't know who said that, but whoever was jumping in there, absolutely, yes. We are going to integrate this thing, absolutely. So that's true. But the basic formula is simply pi r squared. Pi r squared. What are some general guidelines for revolving around the y-axis? And again, I don't want the formula. Let's say instead of revolving it around the x-axis, I ask you to do a problem where I ask you to revolve it around the y-axis. What are some things we need to make sure we take care of? Emily, go ahead.
Sorry. You have to change the x and the y. So if it's y equals square root of x, you got to square root y to make y squared equals x.
Perfect. So we need to make sure that we take our equation, whatever it is that we're revolving, we need to write it in terms of y instead of x. That's perfect. Anything else?
Find big R and little r.
Yep, we'd still need to do the big R and little r. And again, those need to be in terms of y. What's the one more thing we need to be careful of? It's probably going to be given in the problem, but we also need to figure out where we're starting and where we're ending, right? So what we need to know is we need to make sure that we're in y coordinate or y variables. We need to know where to start. We need to know where to end. And we need to figure out and I don't know who said big R, little r. I'm sorry. I'm trying to pay attention, but it's actually kind of hard to do. So anyways, good. Moving on. All right. So how does one handle revolving around an axis other than the x-axis? So let's say up here I said revolve this around the x-axis. What if I said revolve it around the line y equals 12? What do we have to do there?
You would have to change your big R and your little r to match what you're revolving around.
And guys, in my opinion, let's say your curve looks something like this. Let me do blue. Let's say the curve does something like this. And then up here, here's our line. Let's say this is y equals 12, okay? I encourage you, and I've tried to model this in class, draw your rectangles. And I guess that's not a very good example, but we'll go with that. You want to draw your rectangles going like this. So this is f of x, right? So let's say that this is big R. To get big R, I encourage you guys to do top minus bottom. So it would be 12 minus whatever the f function is. That's going to be your big R, for example. Okay? We've practiced all those things, but again, my goal today isn't to actually do a zillion examples. My goal is to kind of just hit some big ideas, okay? Oops. Yeah, last question here. I'm going to erase this stuff. Okay. Oh, I thought I erased it. There we go. That's what I need. Does anybody know where the basic formula for that we use for arc length came from?
Distance.
That's exactly right. That is exactly right, Sam. Well done. This formula for arc length is based on the distance formula. And the distance formula, if you forget, is x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. In fact, I actually posted a video when we did that section on the derivation of this formula, and it comes from the distance formula. That is exactly right. In fact, we already saw the formula on the warm-up. It's going to be, the square root of 1 plus blah, 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 or 1 minus. So, okay. Last chapter that we need to talk about here, big ideas. So this is all new stuff. I would say that probably the most important parts of this for you guys would be this one. I kind of think you're going to see, I'm not super confident on the AP exam how much this they'll have on it. I guarantee you they'll have an integration by parts. I guarantee you they'll probably have at least one partial fraction. And they're probably going to give you some improper integrals as well. So this is actually, I think this is the lesson I gave you guys for this week. Is that correct? Improper integration. And guys, I apologize that we've kind of come to the end of the semester and we're still kind of doing new stuff. If things don't get better, it's going to probably be just as bad second semester. So we're just going to have to go right from January all the way through May 4th to get all in. All right, so let's look at some of the big ideas here. By the way, this here is from Calc AB, so that was kind of review, I guess. I tried to break it down a little bit more. All right, key question. What is the formula integration by parts based on? By the way, does anybody know what the formula is for integration by parts?
Yeah, it's the integral of u dv equals uv minus the integral of v du.
Okay, does anybody know where it came from?
The product rule.
That is exactly right. Well done, sir. This is based on the product rule of derivatives. It turns out that if you know the product rule, which you all do, if you solve that formula, that differential equation, you will get integration by parts. That's where it came from. By the way, I'm not going to, just to let you guys know, these questions I'm not going to ask you on the exam. Hey, where did the formula for integration by parts? It just makes an interesting conversation. Okay, how do you differentiate? That's funny. Using trig integration versus trig substitution. So you guys had a test this week. How did you know when you needed to do trig integration versus trig substitution?
Well, integration is when there are like sines, some degree of sine squared and some degree of cosine squared, or secant and tangent.
Perfect.
And then trig substitution is if you have the certain radicals that you can use for it.
Like, for example, what would I use in this example here, Sam? Let's say x squared.
That would be sine.
Perfect. That's exactly right. So if I had some integral like this, and I don't even know if this works out, so please don't check that. I just made that up. So this is going to be trig substitution. So I'm literally going to plug sine of something into there. In fact, I think it'd be what? 2 sine, wouldn't it? 2 sine theta. And then over here for trig integration, like you said, you might have, sine to the, 3x, cosine to the 2x, and integrate that way. That's exactly right, Sam. Very good. All right, basic idea behind partial fractions. What's the basic idea behind partial fractions?
If the denominator is a product, you can separate the fractions into 2 different fractions.
What's your cat's name, Lisa?
Sorry, my cat's name is Domino.
Hi, Domino. Yeah, you're exactly right, Mason. So when we're this partial fraction thing, think about it this way. If in the past when you've done maybe something like this back when you were in like middle school or whatever, what would you do? You'd get a common denominator, right? So this would become 3 times 5, and then this would be 2 times 5 plus 3 times, anyways. So this is how we get this answer, which what would that answer be? That's going to be 10 plus, so that'd be 13 on the top and 15 on the bottom. So this is what we did in the past, back when you were a wee child, and now we are going backwards. So that key idea that Mason mentioned here is if you've got a product, and of course these are algebraic, and then a lot of times when you're doing these things, you're going to use log integration to deal with those. Okay, really important question. What must first be established before you try to use L'Hopital's rule? I tried to emphasize this last week.
Has to be an indeterminate form.
In particular, which one though, Hunter?
0 over 0.
Perfect. So remember, and I don't know if any of you guys watched that video. There was a video I posted that I did not make, and I said, you got to watch this. Raise your hand if you watch that video. It's a great video. And basically the, and I can't think of his name now, mathologer, he basically shows that all of these different indeterminate forms are essentially 0 divided by 0. But when you look at L'Hopital's rule basically is predicated that you are given 0 over 0, which is an indeterminate form, because 0 over 0 can literally be anything. And actually, you can almost boil everything down in calculus to this right here, this whole idea of whatever 0 divided by 0 is. What makes an integral improper? Last question on this. What makes an integral improper?
Basically, if you have to take a limit in order to solve it.
Yeah. The biggest idea is this. In general, if we do a definite integral, we are doing it from some A and some B that are what? Real numbers, right? Like from 2 to 7 or whatever. An example of an improper integral is if, let's say, B was infinity, because guess what B is not? A real number. Thus, that makes that an improper integral, and we have to use something called a limit. There's one other reason that we need to do improper integration. Can anyone think of another example besides the fact that A or B is infinity or negative infinity?
Discontinuity.
That is exactly right, Ridge.
Sorry for talking over.
Huh?
Someone else.
No,
I'm talking over someone else. Sorry.
You're fine. The other issue is if we have a discontinuity somewhere in the interval. So you may have something like -1 to 1 of 1 over x dx. And someone in Calc AB next semester, when we get to chapter 4, they might see that, but oh yeah, I can calculate that integral. Well, what's the problem? Well, we have a vertical asymptote at 0. In fact, I'm pretty sure, I don't want to speak, but I don't even think this has an answer. I think that this is D and E. But this is an improper integral because we have a discontinuity at 0. We have a discontinuity at 0. And it's a bad discontinuity because it goes to infinity and negative infinity. Okay, so now here's where I'm going to stop. And I'm going to just kind of pause on section 7.8. Does anyone have, and man, we're already 5 minutes left here, so I'm going to go. Do you guys have any quick questions that you'd like to ask me about 7.8? Okay, so I'm going to go ahead and move on. If you have a question, James, yes.
Never mind, it wasn't on 7.8.
Okay, all right, I'll come back to, I got more things to do. And remember, we've got about 5 minutes left. Once we hit 45 minutes, if you need to go, you are allowed to go, but I'm going to keep going. Anyways, I can do questions or examples of improper integrals if you would like. I figured you guys needed maybe the review more so than just the one section of practice stuff. All right, please do not forget that you have your last web assign for this semester. It's due tonight at 9 p.m. Please do not forget to do that. You guys do a good job of that, but I just want to remind you one more time. Okay, so test questions. I had a few people email me and say, Mr. Allen, can we spend some time going over test questions? The answer is yes. I'm not going to do that just now. But what I did is I went ahead and I just basically printed out a copy of the test and I worked them all out. So if you have questions about one of those or several of them or whatever, if we have enough time, I'll be glad to talk about those. And I just want to let you guys know, the tests are graded, and I try to grade it very generously. I'm just going to be completely honest with you. The last test we took, I kind of felt like it was a little bit too easy. So this one I made a little bit more challenging, and you guys might be shaking your head. Yep, that was a little bit more challenging, Mr. Allen. Guys, I'm sorry. It is what it is. It was probably a little bit harder than you were expecting. So I tried to grade it very generously, and I hope that you can live with that. I'm learning how to do this whole online thing just like you are. And I just figured, it's online. You guys can use your calculator. You can use your notes. I figured, hey, let's make it interesting. And maybe I went a little bit too far on that. So I apologize if you've been stressed out and I hurt your feelings or whatever. That wasn't my intent. And anyway, but I'll be glad to take any questions on the chapter 6-7 test if you'd like, because everyone's taking it now. By the way, I would like to commend Lisa Harrell. Lisa, if you were here in person, I'd be giving you the literal gold brick today because you were the only one. You were the highest score on that test. You didn't get perfect, but you only missed one problem, which is pretty amazing. And let me just say this. Sometimes knowing how to take a multiple choice test is is very important as knowing all the calculus, right? Sometimes you may not know what the answer is exactly, and you need to learn how to reduce some answers. But yeah, let's go and give Lisa a real quick round of applause. Let me get that gold brick up here. Lisa, today is December the 11th, and I'm awarding you this gold brick, even though I can't actually give it to you. You've earned it. Good job on the test 6-7, which is by far the hardest test we've had all semester. So good job.
Thank you.
You're welcome. Okay. Actually, let me say one more good thing about Lisa. One of the things I like about Lisa, besides the fact that she's a really good math student, is she is very humble and very polite, which is awesome. So keep doing what you're doing, Lisa. You're doing great. All right. I have posted on Canvas, we've got about 2 minutes left, a review of semester 1. And you might have noticed the other day I put 3 through 6. It's actually chapters 2 through 6. I've updated that when I started looking through there. There's actually a couple of limits on there. This review is has anybody started that? Has anybody started playing with this thing yet? It's a lot. I'm just telling you, if you don't do all of this, it's completely fine. I just wanted to throw that up there, and I'm going to post the answers later today with work and all that, just to give you something to review. I would encourage you to do some of the problems, but there's way more there than I should have put on. And again, I get a little bit ambitious with this. So anyways, there is a review, and I'll be glad to take questions on that later if you'd like. So we're down to a minute. Okay, so here's what we're going to do. You guys, we're going to get a poll here. I'm going to stay on here. We got about a minute left. I'm going to do a very quick poll. And on the poll, I just want your feedback. What are you doing, Gavin? Sorry, I'm trying to type and read your thing at the same time. What's going on?
I'm going to stream that entire review because I need it just as much as you guys do.
Okay, cool. Thank you, Gavin. Let's see here. Thank you, Gavin. Okay. I am launching the poll right now. And at this point, we are at the end of the time, the 45 minutes. So if you can't stay or if you don't want to stay, you're not going to hurt my feelings. I need you to decide if you want to stay and review for about another 30 minutes. Would you rather do a Jeopardy game or would you rather play Kahoot? I really don't care. I've got both already made and ready to rock and roll. So please just take a minute to vote.
Mr. Allen.
Yeah.
I have a quick question.
Yes.
So for NVT, are we gonna have to know both the NVT of the integral, like the integral NVT and the derivative?
You should be aware of both. So MVT for differentiation is basically saying that the instantaneous rate of change is equal to the average rate of change. But then when you do the MVT for integration, that's basically just saying that the area of the rectangle is equal to the exact area under the curve. So yeah, you do kind of need to be familiar with that. Guys, I'm just kind of pretending like this is like a normal year, and I know that's not fair. Just know that guys, raise your hand if you feel like I take care of you in terms of your grade. Guys, I want you guys to be the best that you can be. But if you fall down a little bit, I'm going to help pick you back up. So don't stress out too much. But I would encourage you, and I'm going to speak specifically to you, James. James, I get the sense that you want to go to a STEM career maybe and go to a college where you're going to be doing STEM stuff. And I'm just telling you right now, there isn't anything that we've done in this class that I'd say you don't need to know it. The more you know about this stuff, the stronger you're going to be when you go to the next level, particularly if you're going to get into like engineering or something like that. So, all right. So it looks like some people are leaving. That's fine. I'm losing my voice already, and I've only taught 2 periods today. It looks like the majority of you would like to play Kahoot. So that's what we're going to play. You are welcome to stay. We're going to play till about 10:45 or less. And then at that time, I'm going to break off because then I need to eat lunch, and I've got a bunch of stuff that I've got to get done. So, and I'm not trying to be rude. Oh, don't forget makeup work. All of that stuff is due today at 9. So without further ado, I'm going to turn off the recording.